2.56. And then this guy, Galileo, comes along with his telescope, and he discovered a lot of interesting, a lot of really cool stuff. Particularly, he's recognized for the Galilean moons around Jupiter, so for discovering those, which are very easy to see in any low power magnification telescope. But he also maybe less known, was looking at, when he started looking at other stars, or he started looking at other spaces in the night sky, he started noticing that on top of the 6th magnitude, the really dim stars that he was looking at, he was also seeing a lot of other stars, dimmer stars, which he referred to as the 7th magnitude stars, right? And this was just dim stars that you could not be seen with the naked eye, can now be seen with the telescope. So now we have an extended range on top of this. And as we know today, that extends way off. We get down into some very, very dim magnitudes using a lot of telescopes. And so like maybe some examples of this. Now this is where that silliness that I was talking about comes into play. So the result of making the brightest star meant that some interesting questions came up, like, well, how do we rank a planet like Venus or the Moon or even the Sun, right? And the only way to really account for that was to have negatives. So really bright objects are really negative. And also, you can see that things, we've gotten down into some really dim, objects. So things like basically the faintest thing we can see is about 30. The limiting magnitude of like a 10-inch telescope is probably around 12 magnitude-ish stars. Might be a little bit off on that, but you get the idea. Just to give you some other examples. Just a few stars. So when you're looking, if you're ever looking at an object in a catalog or anything like that, and you want to have an idea of how bright is this thing, the magnitude number is the one that you want to look at, right? That HD 216932 is a named star, has a magnitude of 9.1. So that one's quite dim. It would be outside of your visual range. You would not be able to see it with your naked eye. But you would be able to see it with probably a 8-inch scope, kind of thing. So this will give you an idea of what those ranges are like. So one of the kind of funny things about ranking these objects, ranking these stars in brightness in the ways that they did, was that in ranking the objects in the ways that they did, is they identified something that has become known about the human body and how it operates. This applies to things like how our eyes measure brightness, and how we detect sound, and actually how we count. And that is that our brains work logarithmically. So what that means is, for every, so 1 to 2 is actually more like 1 to 10, 1 to 3 is actually more like 1 to 100. And so the way that the brightness started working, so what happened was they started looking at, sorry, this is really bad just because of the way this is set up. I know my notes, so I'm trying to remember everything. This is a really bad idea. So the way that the magnitudes work is that we looked at them and said, okay, 1, 2, 3, 4, 5, 6. But when you actually started measuring how bright these objects were, our eyes are not actually very good at being able to judge that. So in actuality, a magnitude 1 object is actually 2.5 times brighter than a magnitude 2 object. Similarly, a magnitude 1 object is 100 times brighter than a magnitude 6 object. Okay? So this is just a result of how our eyes work and how they are logarithmic. So if you want to see this in tabular format, just if that helps at all. So when we talk about brightness, we've just been talking about just the pure luminosity of it, right? So how much our eyes are seeing in that. But there's another component to it, which is star color. So when it comes to star color, if you look up in the night sky, you'll actually see that stars have a considerable variation in color. So things, from red to white to blue, and so we need ways of actually measuring those. And the classically accepted system is the UVD photometric system, and we don't need to get into the details of this, but what we're looking at are basically a set of color magnitudes. So where are these stars brightest at a certain wavelength? Where are these stars brightest at a certain wavelength? So what does that mean is we're gonna take that wavelength and use it to classify this star by color. And so one of the ways that we do this, just as kind of a convention, is we take the blue minus the visual, and that gives us a number. And what that number means is just this is its color index. It's kind of an arbitrary thing, but it is a number that allows us to, again, classify these stars into a bucket, right? So a type of star. So, just for some example, a star which is brighter in B, then in V will be a blue star. For a pure white star, the B minus V is equal to 0.2. For our sun, B minus V is 0.61, and so on. So these are just numbers. You don't really need to worry about those too much, but just know that the system is there and know that those numbers represent. So, up until now, when I was talking about magnitudes and brightness, I was talking about apparent magnitudes and brightness. So, if we're going to talk about apparent magnitudes, it's not entirely useful, right? I mean, if you're going to actually if you want to look at what are the properties of these stars, so what we're maybe more interested in on the science side of things is what are the absolute magnitudes of these objects, right? So, for instance, I think that actually this is such a great example because Sirius is the brightest star in the sky. But if you look, I don't have a laser pointer, but if you look at where Sirius is in the left, that is how bright it appears to us. Oh, thanks. So, Sirius right there on the left. So this is the apparent magnitude, right? This is how bright it is as we see it. Now, intrinsically, right? So stars come in all different in different sizes and brightnesses, right? Sirius itself is actually a fairly dim star in comparison to all these other ones within its constellation of Canis Major, right? And that's just a result of us being further away from these stars, that we don't see these as bright. There are various things like dust and whatnot that get in the way. And to give you some other examples, so if we compare, like our sun actually has an absolute magnitude of 4.58. Arcturus is about 0.29. So you can kind of compare these numbers to see that there is a bit of a difference there, right? And there's going to be, and that difference is going to be based on how far away we are from it, right? Now, one of the weird things about an absolute magnitude is how do you actually define an absolute magnitude? And it's kind of arbitrary again. They've defined it as, I think the distance is 10 AU away from the object. Parsec, sorry, yeah. 10 AU is way too close. Sorry, yeah, so it's defined as 10 parsecs away from the object. And that's just kind of like it's a nice distance to be at, where the object is not too bright, but it gives you a standard distance that you can then use to judge all other objects. So, getting back into colors, and whatnot, and actually just star properties in general. One of the things that started happening in the late 1800s, early 1900s was we developed the ability to actually look at the spectra of stars. So this is looking at stars and using spectroscopy to basically analyze their elemental makeup, right? And this is a really powerful tool, and what it allowed us to do was look at all the stars that are in the sky and start cataloging them, and then not just take these, so previously we've been doing it with things like with brightness, right? We've been cataloging them based on that, but now what we're actually doing is we're cataloging them based on spectra, and that has allowed us to really look at a large set of data and given us the ability to see how stars are different across the universe in a wide variety of ways. So, yeah, the classic. So back at Harvard, it was interesting. They had a team of women who were actually collecting all this data and analyzing it. And actually did some amazing work that kind of went unrecognized for quite a while. But anyway, so as they were collecting all this spectral data from these stars, they classified them into different spectral classes. Okay, so the letters, because they didn't know how these spectral classes would actually shape out, the letters in the end didn't end up making any sense. So we kind of ended up in the same way that we do with our negative magnitudes. It's the same kind of thing where we get stuck into a certain way and we just refuse to pull ourselves out of it and change anything. So it's like, oh, these are the classes we have. These are the ones we're going to use. So these actually go in order. These go in an order that will make a little more sense as we move along. But this order is actually very specific now. But in order to remember it, they use the mnemonic OBA fine girl guy, guess me. Which works. It really does. I remember this in my first year astronomy class, and I've never forgotten it. But hey, yeah. So, but the thing to keep in mind here is that what we're talking about here are when we're talking about these spectral classes. So we're talking about the blue stars that you see, the blue-white stars, and the white, the yellow-white, yellow, orange, red, and this will come together in a few slides. So just keep that in mind as we're going on. We've also got some other, if you really want to get into the depth of these spectral classes, there's an expanded system called the Morgan-Keenan system that is actually the one that I see more common. Like I see, we use it pretty commonly. So like our sun is a G2b star. In plain English, that's a yellow 2/10 towards orange main sequence star. It's like white English, but it's closer you're going to get to English when you're talking about this stuff. So, yeah, so it's just a way to. The point I wanted to make was just that we can break down these spectral classes further and further and further. And we got 2 minutes, so we'll probably finish off on the HR diagrams today. So, taking all this Harvard data that was collected, 2 astronomers, Hertzsprung and Russell. Hertzsprung was a Danish guy, and I will not try to pronounce his first name because he's Danish. And believe me, if you've ever met a Dane, you can't speak Danish. Don't even try. But they took all this data and independently they tried to plot it, right? So just imagine we've collected all this spectral data, right? And we've cataloged it, but we've not tried to really do anything with it up to this point, right? We haven't, well, I mean, we've tried, but we've not been able to come up with anything. And what they came up with, independently, was if you plot, these are all the stars that we have data for, okay? If you plot luminosity or brightness on one axis, and then the spectral class or temperature or color on the other axis, you actually get this amazing collection of data that looks like this. And what this does is it shows us how stars fit in together and how they're different or similar, or how they evolve. So the main points, we'll discuss the main points along this except I've kind of run out of time.
Next week we start.
So yeah, I barely begun on the HR diagrams. Yeah. So anyway, I do apologize for that. That was not the way that I wanted any of this to go. But yeah, so I will return to this within a month, and hopefully we will have our system work better next time. Thanks.
Brandon? Good luck with the HR diagrams. I was hoping you'd get a little farther, because I wanted to talk about them a little bit last
What's new? Brandon's actually at the maybe. Hey, what's up, Ryan?
Can I do in fact, I better load it up pretty quickly because you're right after me. Okay, Brendan, where's the... Who's still here? Where it is? Yeah, well, we'll have to start one of these days. Okay, how are we doing here? Oh, that sounds better. I can hear myself think.
Yeah.
I think Bill Gates has finished updating everything now. What held us up mostly was the sudden decision that Office had to be updated. Well, we've already heard from Brendan with the promise of more to come. You know, the subject of stars takes about a whole term or maybe 2 terms in university, so you've at least got to be applauded for trying. Hertzsprung Russell is probably 2 weeks by itself. but it's one of the most powerful graphs in all of astronomy. And we'll see a little bit of it, how it's used today, and some of the other things coming up. After announcements, Brian Statch will be telling us what's coming up for the next month in the sky. They'll get us out in what I hope are warmer temperatures. I was ready to tell the media not very long ago that we were finished with minus 30s and now the minus 29 forecast for tonight. So it won't be the first time I've been wrong. After Brian, I'll talk about what's new, and of course the big subject in there is the detection of gravitational waves, which has actually far more astronomical significance than has been coming out generally in the literature, in the newspapers and television. They're all talking more about the delight of the people that found it, which is certainly very valid, but there was also some rather delightful science in it too. Gail Wise is going to talk about my favorite constellation. So that's my sign. Which might account for some parts of my personality, I guess. First of all, I sent this note out to everybody, but the magazine, Astronomy Technology Today, which how many of you read it or at least signed in for it? Yeah, a few this year. That's a pretty classy magazine in the sense that if you've got leftover cash and you don't know what to do with it, all of the new stuff that people are building is usually presented in Astronomy Technology Today. And they are actually offering members of clubs free subscription to this for 1 year. And you'll find a lot of useful information in it, but mostly you'll find stuff you want to drool over because everybody who's anybody that's got something for sale in astronomy is in this thing. So what you do is you go to the astronomytechnologytoday.com and you go to subscribe, and in the box that comes up, one of them, you type in the coupon or something like that. And you type in the word club, and up comes another, email. Oh no, you select the kind of subscription, which is a 12-month electronic subscription. Then you go to a page and stuff to fill out, name, address, email, that sort of thing. It also has a $12 price on it. But as soon as you fill that out, because you put the word club in, the $12 disappears on the next page. And when that's done, you just click send, and seconds later you'll get an email that says what your password is, and from that you can go in and start reading all of the articles for the next year, plus anything that's been done and written in the past. So if you're thinking about buying a telescope, you might be able to actually find some reviews of that telescope and how it performed, or you get hints on how to make things work a little better, and so on and so forth. So they sent this to me today and asked me to spread it around, and I did send it out generally to the group 2 days ago. I know some of you have subscribed already to that. Not very often you get free stuff. Of course, you know in a year is up, you're going to get a request to pay the $12 a year subscription fee, but that's legitimate as far as I'm concerned. If you like it. University of Manitoba Faculty of Science has a speaker coming to talk on March the 3rd under the title of Brilliant Blunders. And you can see on this how mistakes by great scientists changed our understanding. Well, they're getting Mario Livio coming in, who is, I know the name, and anyway, he's the author of this book on blunders. So if you want to hear him speak and buy his book and get it signed, then there you go on March the 3rd in the Robert B. Schultz Theater next door to us over here. So it's at 3 p.m. Well, there are 2 dates here. One at 3 p.m., one at 10 a.m. 10 a.m. one is over in Arms, which is one of the big theaters on the other side of Canada. So you come to the afternoon one. Particularly like the word refreshments to follow. The university usually does pretty good, but you have to get out there quickly. So he's an astrophysicist, got his time in on Hubble, and actually 400 scientific articles. Well, that usually means he published 50 and his grad students published 300. So he knows that. Tomorrow, members observing night. Anybody check the weather? Light snow. Well, probably won't be a members observing night tomorrow, but Brian, well, you can make the decision for yourself. If it's snowing, telescopes don't work in the snow. Well, radio telescopes do, and so do gravitational telescopes. Astronomy Day. I just wanted to give you a heads up on this. On May the 14th, we're going to be looking for volunteers. There's another, certainly by the April meeting. Most of you are familiar with the process. We'll set up a table at one of the shopping malls, likely over by Chapters there by Polo Park, which is where we've been doing it in the past. And then in the evening we'll have a star party out at Assembly Park for the public. And so we like people to come out with their telescopes and show the starry sky that folks live. We'll have Jupiter up nice and high on that date. I don't know what the moon will be, but it looks like it should be around first quarter. It follows the usual pattern all around the Earth. And I'm not sure, Saturn probably rises around 10 or something like that. It might be a little too late to get high enough up to see. The open house at the Telescope and Planetarium that you have been having on the first day of each month is on, it's being paused for the time being until that can be reorganized. No, it wasn't. Telescope loan, Stanley, you'll be here. Is he it? Is there still one available?
There's one available.
There's one available now. What is it?
It's an 8-inch dog.
8-inch stop is available for loans. You see the stand if you want it. There's no charge for borrowing a telescope. You get it for a month for sure, and if nobody else expresses an interest in it, then you keep it for a longer time period than that. And Glenley Observatory is open to everybody. It's been getting a little bit of use. Brian will be saying something about some upgrades to the observatory, but it's 15 kilometers south of the south perimeter down the Pembina Highway. It could be darker, but it's darker than inside the city. You can actually see the Milky Way out there, especially in the summer when it's Milky Way. There's a 14-inch daub out there too that can be used. It's a little bit of a bear to put together because it's pretty heavy. But once it's done, it's a nice little telescope to use. If you want to see Brian, who's at the middle back, and he'll be talking in a minute, and he'll give you the details on that. Sylvia, where? I know you have my slides here.
Hi everyone. Marnie Dangerfield asked me to make this announcement for her tonight. It's about the Fort White dinner and a show event. You're probably familiar with it. It happens every year around this time. And this year it's happening on March 19th. It's on a Saturday. Basically it's Fort White Center delivering a gourmet meal to people who buy tickets to attend the dinner. And the RASC members will deliver some astronomy talks. So if you're interested in volunteering, bringing your telescope, and participating with us, let me know, and I can get you in contact with Marnie, or just contact Marnie directly. And again, it's March 19th on Saturday, and we're looking for a handful of volunteers if anyone is interested. Thank you.
Food and astronomy, it's kind of like these meetings with the departure over to Boston Pizza afterward. I guess I'll turn the floor over to Brian now because he's got two subjects that he wants to discuss. I'm guessing you'll want to go with this one first. Sure.
Is that better? Better. All right. Okay, so I'm Ryan Statch. I'm the director of Glen Lee. I'll show you what I've done so far for the upgrades. Hit the space button. All right, just a quick update. So for Glen Lee, we have the Means LX200 there. Also, we have the 14-inch Newtonian. That's a truss-designed telescope, but you need to set it up first in order to get it to work. What I was hoping to do when it warms up, I'll set it up permanently so you can just roll it out. Now, what I've been working on, that network junction box where you can plug in your mount and use the warm room through the other network junction box. So I'll show you later what I mean by that. So you can control it from within the warm room. And there will be, of course, everyone knows you have to use the network cables. Now, for the warm room, what I've done right now is I upgraded the computer I have there for Windows up to Windows 10. I prefer a little bit better, but I do have Solarium and some old Starry Night software installed on it. Of course, you have to see me about the keys. What I like to make a point out is that the dome is rated for -10 degrees. Anything greater than that, you can't really use it. Okay, what else do I have? For booking and training, I left my phone number and my email, so if you want to book to be trained or to use the LX200, please contact me first. Of course, we have some charts, microwave ovens, there's some coffee and some hot chocolate there. Now, I'll show you a little bit more. I left the hair dryer and extension cord. So if you want to defog or defrost your equipment while you're out there, please do. Now, I'll show you. Right here? Oh, pencil one. All right. Okay. So we have a really nice. But I do have a printer there, so I need some ink, and I have to install it. So I didn't really even want to mention that. So we have a nice little monitor there. That's the conjunction box, the network conjunction box. This is the one on the pad. This is the one in the warm room. So you'll be able to plug in all your equipment through on the pad, and then plug your laptop here, or use the computer if you want to, and then control your mount from there if you want to. All right, now just kind of like, I didn't have time to complete everything, so this is our barbecue. So there's the Glen Lee right there. We do that once a year. Now this is inside. This is the LX200. Very nice telescope. If you want to, I don't have the cables with me, but I'll start leaving the cables here. I do have some cables I spliced together. So you'll be able to take the LX200 and connect it to your laptop and control it from there. But you need to install the USB drivers in order for it to work. And I think that's all I really have for Glen Lee for updates. I'll have more later on, so that's outside right now. And I'll take care of the Glen Lee updates. I guess I'll do the what's up now.
Yes, you're up, sir.
All right, let's start with this.
Let's do an alt tab.
Well done, Brian.
Yeah,
Well done.
okay, all right.
Hey, you mowed the lawn last week, too. F5.
Okay, so I'll tell you what's up for February and a little bit of March. Okay, so we still have the 5 planets. Of course, Mercury, Venus, and Saturn are mostly in the morning, but Mars starts to rise around 1 a.m., and Jupiter pretty much dominates most of the night. Next slide here, I like showing this one here. It kind of gives you an idea of where the planets are in relation to Earth. Again, we see Mercury and Venus as your morning planets plus Saturn. Then we have Mars, and then we have we have Jupiter. Okay. Now, pay attention because I'm going to show you more about these zodiacal lights. Zodiacal lights there. That's going to be mentioned a little bit later. Okay, so here, this is for February the 14th. Just to give you an idea of what constellations that we have up there. There's Jupiter, and that's roughly about 2 a.m. in the morning. And also showing that Mars is there. It rises about 1, but I think more like 2 o'clock you'll be able to see it then. Now for the next slide, I'm trying to show you this, but maybe I'll show you again on the next slide. You can still see the 5 planets. So we have Jupiter here, we have Mars, we have Saturn, and then we have Mercury and Venus down here. Now this is roughly, of course you can see the sun starting to come up. So it's, here it is. So it's about 7:16 a.m. on February the 13th. So that's roughly about 2 hours, right? So you can still see it, but it's going to be kind of close. Now for the calendar, special calendars, we have, of course, Mercury, its greatest elongation. We have new moon on February the 8th. We have the full moon on the 22nd. Of course, we have, what's that kind of nice, or I like to call it, what's the double shadow transit for Jupiter on the 22nd. Now these are the times, universal times, of when they actually show up. Next we have where the conjunction between Moon and Jupiter is on February the 23rd. And next we have on February the 24th the zodiacal lights are going to be coming up for the next 2 weeks after February the 24th. And of course we still have showing up still. Now what I've done here is just kind of give you an idea of what's happening between Jupiter and Moon. I try to play around with the end here. So basically, it said February the 23rd, but closer to midnight, that's where it's going to get the closest between those Jupiter and Moon. But it's going to pretty much dominate February the 23rd in the evening. Now, for the zodiacal lights, we explain a little bit more about what it is. Of course, it's an interplanetary dust cloud. Basically, they're about the size of a pebble to really fine pebbles, probably like the smallest wavelengths of light. So what, 103 nanometers, I would say. How they appear as a soft white pyramid of light, whereas the base is more towards the horizon and the point is towards the elliptic plane, which I'll explain more about what the elliptic plane is for the newer members. What else do I have? Okay, and of course, when do we see it? We see it usually in the spring and fall, but it's when the geometry is right. Now, for the months of February and March, it's going to be towards the evening. It's going to be about a half hour after the twilight. That would be the best time to see it. In the fall, it would be a little different. It would be towards more of the morning. Okay, best time to see it would be, like I said, half hour after the evening twilight. Can I give you the idea of the brightness of the zodiacal lights? Of course, unfortunately, we do have competing with the moon on February the 22nd. So if there's some moonlight, haze, or light pollution, that's going to rule out some chance of you seeing the lights. Now, I kind of mentioned about this, about the evening dark. Even for the most experienced astronomer or inexperienced astronomer, they might confuse the zodiacal lights with either the twilight or the light pollution. Now, I did some calculations to see if the moon is going to interfere with it, but it shouldn't actually. We'll get a chance to see it just before the moon starts to rise. Okay, now this is the edge-on view of the zodiacal lights. We have Jupiter here and Saturn. Now, this dust here is actually made up, it's maintained by asteroids colliding, as well as the dust left behind from comets as they pass through the solar system. But when I learned this a couple of years ago, they're thinking it's the dust left over from the creation of the solar system, but that's no longer the case. Okay, now I want to come back to this one here, because this is where we are at evening twilight here. So actually we're seeing the dust lanes here. Now this is Gemini here, this is Taurus here, the constellation. So there's Jupiter. So right about here, that's what we're seeing. Just going to give you an idea. Now, for the elliptic plane, for your newer members, okay, this is the path that the sun takes across the sky. So just to bear in mind what that is. Now for the next slide, what I've done here is, this is going to be a half hour just after the twilight, which is supposed to be 1920 or something like that, according to the book. So there's the elliptic plane there. That's the path that the sun takes. So right here, I think that it's going to be from here to here. So you got your point here, and you're going to have the widest point right about here, I would say. I don't really have any pictures, because I haven't seen it yet, actually. Now, just to kind of give you an idea of what it may look like. So we have these vertical lights here. There's the Milky Way. That's your point. Actually, we got a little bit of light pollution here, but it's going to be different. There's your geometry plane that we talked about. It's relatively a steep angle. All right, here's another shot. Just to give you an idea. There's your pyramid right there. And there's another shot there. Just kind of give you an idea.
Going too fast?
All right, now I want to come back to the comet. Of course, it's moving away from us. All right, so as it moves away from us, the two tails are actually going to start to merge once again. Now there's, thanks to Sheila, that's a picture of Angelina. I think that's the star Taurus, I believe. And she took that picture. Now, so on February the 14th, around midnight, this is where it's going to be. This is, there should be Polaris right there, and this is constellation Camilo Pardalis, and there's the two stars Alpha and Gamma. So right between there, that's when you find your comet Catalina. Just going to give you an idea of where it's going to be next time. Now, here's an idea of the projected path for the next spread to February of 2017. All right, so this actually continues on where I left off last time. There's January, there's February the 14th, there's March, I think this is supposed to be September, October, and then that's February 2017, to give you an idea of Catalina, the path is where it take. Now, the next question is, I took this one here, I don't know how it's going to work out, you guys will be able to see it. So I took two shots of it. Okay, now for the magnitude of it. Did some calculations here for February and March, trying to get the idea. This is the what people observe for the magnitude. It varies from either a telescope, a Newtonian, a reflector, or some binos. So this is what they report it to be. This is the predicted value of it. So you can see pretty much by March, it's going to be, I think, pretty much out of our reach. Unless you have a really big telescope. Okay, now for the next October, you can see again, it's going to pretty much hit by, the magnitude of 15 by September. It's going to be probably unreachable. It's going to be pretty much unobservable there. So, still want to get out there. It's going to be kind of cold probably, but anyways, try and take a look at it. We still can. All right, and I think that's it. Is it? Yeah, that's it. That's all I have for you guys.
A little bit of cheesecake there. Well, kind of got scooped by every newspaper in the world 2 days ago. I think I've found a few things, but there are a few things out there that you might be interested in with our first story, which is, of course, the detection of gravitational waves. Now, Einstein predicted it in 1916, and we're finding it in 2016, so it's kind of an appropriate interval of time, but the first detection of gravitational waves, at least, gravitational rage, that could be quite something, a wave, anyway, was detected by these two fellows back in 1974. And what they did is they were observing a pulsar neutron star binary. and they found that the orbit of the two stars, which are very, very dense, very condensed objects, but not quite black holes, but the orbit of these two is gradually shrinking. And it was shrinking in their hypothesis because they were losing energy in some fashion. So they calculated how much gravitational energy a star system like that should be losing. And lo and behold, it exactly matched the loss of energy that they were seeing in their observation. So they said, this star is losing energy because, or the two pairs of stars, pair of stars losing energy because it's radiating gravitational waves. And they actually won the Nobel Prize for that. So from a scientific point of view, this was probably enough proof to conclude that gravitational waves existed, but not detected. And so that's what we've done on September 14 last, the Advanced LIGO detector, which we'll talk about a little later, detected this gravitational wave.
The other one says something.
Ah, there it is, okay. So anyway, they have two LIGO observatories. The reason being is that there's so much noise in the signal that they're trying to detect in the environment in which they're trying to detect the signal that they wanted the second one to verify the first one. It's unlikely that a passing train was going to be going past both of them at the same time. What kind of a detection level are we talking about? Well, we're talking about a displacement less than, by a considerable magnitude, less than the diameter of a typical atom. So we're not playing around with little tremors from a truck going by like the seismologists have to deal with. We're dealing with something quite a bit more. As it turned out, the scientists that were putting this together worked late on the night of September 13 to 14, trying to tune the last little bits of noise out of the system before they officially turned it on, which I believe was scheduled for September the 18th. And they went home at 4 o'clock in the morning. They just run out of energy. At 4:50 in the morning, that signal was picked up by a machine that wasn't quite ready for operation. And I had it set up that when it detected a potential target, the computer said, hey, here's something here, and sends a text message out to the scientists, the 3 scientists who were most involved with this thing. None of them were reading their text messages that day. And 2 days later, they said, oh, hey, it's been detected. But you see, in order to test this system, they actually have a team that injects fake signals into this apparatus in order to see how well it's working and whether anybody's on their toes. And they said, oh, well, it's the testing team injecting an artificial signal. And a day later, they met up with someone and said, well, you know, we didn't respond to your artificial signal. Well, we didn't send out an artificial signal. And then, of course, they went in and it was, wow. And that's what they saw. And here they are. This one is superimposed on this one. So this one's in Louisiana and this is in Washington. It's very far apart. The only thing common between them is this wave train. This is a calculation of what the wave train should look like. It took, I think it was 6.5 microseconds for this thing to go from one to the other. And here we see a frequency time signal of this thing. And basically what this is showing is what you see here, is that the frequency gets higher and higher as you go higher up in the graph. And as time went on, the frequency which was lower here, these waves, got higher and higher frequency, and they moved up onto the chart, and they also got much stronger. And the second observatory, a little bit less signal-to-noise ratio on that signal. This is the only observational detection of a black hole. Up till now, a black hole has been a theoretical idea, a modeling idea, an idea where we think we know what it should look like on the outside of a black hole and we see that. This is the actual detection of a black hole. So this is the best evidence so far for the existence of black holes. It pretty much confirms it from a scientific point of view. Here is a sort of reconstruction of cleaner modeling of the signal based on what they saw. And here we have a graph that shows you the velocity on the top line. So this is the velocity of these two stars going around each other. They're starting off at somewhere around 7 or 8/10 the speed of light. And that gradually declines as time goes on. This is the separation of these two stars from each other. Sorry, I got it the other way. This is the separation. They're getting closer. This is the velocity. And as they get closer and closer to each other, their velocity goes up until they're approaching 6/10 of the speed of light. The real story in here is this. During this wave thing, you have, they call it in spiral. It almost looks like inspiration. In spiral. This is the two black holes spiraling in toward each other, getting closer and closer until at this point they merge, and then the wave collapses, and then you get several more waves, and this is what they call ring down. So what's happening is these two stars start to merge at this point, and at this point they have merged, but they're inside the Schwarzschild limit of that surrounds them, the limit at which light cannot, or inside the Schwarzschild limit, light cannot escape from the black hole. So this part of the signal is actually coming from inside a black hole. At the time that it reached its highest frequency, they were orbiting at 75 hertz, 75 times per second. These stars were orbiting around each other. And of course, generating the gravitational waves, there's ripples going out from this very quick oscillation around each other. They were within 350 kilometers. Of course, being black holes at the start, they both had a physical dimension that was much smaller than that. And so until they combined and merged together here, and then that's the end of the gravitational wave coming out. There's now a spherical body, and of course there's no oscillation going around each other. Now if you calculate 75 hertz, the speed of light, a little math will tell you that the wavelength when it was at its highest frequency of these gravitational waves was around 4,000 kilometers. The nice thing about gravitational waves is it doesn't matter if there's a great big body between you and the source of it. They just sail right through the universe, through the Earth and everything else. So in fact, this event occurred probably in the southern hemisphere somewhere. So what's really significant about here, it's nice to see gravitational waves, but what's really interesting is what we can see astronomically because of the signal from this thing. And of course they're starting to say, well, we can analyze this in here now with a little bit better signal-to-noise ratio. Signal-to-noise ratio on this is huge, it's 25. And they still haven't reached the maximum sensitivity that they can get with this machine. So they may be actually able to determine at some point what the rotational velocity is. But right now they can calculate it from these parameters in the modeling that they've done. So one of these black holes had a mass of 36 plus 5 minus 4 mass of the Earth. One was 20, let's say 36 and 29 times the mass of not the Earth, the Sun. So these are big stars. We never thought that a star that big could form a black hole because normally stars that big blow off a lot of their mass before they turn into a smaller black hole. So right away we learned something that the size limits we thought we had of black holes is much bigger. The final mass when the two of them combined is 62 times the mass of our Sun. It's got a spin rate here. Its mass is, no, we won't worry about that. What else is important? Redshift is about a 0.09 redshift, 1.3 billion light years away from us. I say years. Well, it is 1.3 billion years away from us too. So, only 4.6% of the energy that was contained in that orbit is converted into gravitational waves.
Can I ask a question?
You expect to get an answer that if it doesn't involve higher level math, yes.
So the difference in mass between the final total mass of the black hole and the individual masses of each of the components is radiated into gravitational waves.
Well, I think you'll find the uncertainty in the mass estimates cover it off. So they all fit within the envelope. So certainly the radiation of energy from this thing would not necessarily have come from any conversion of mass to something, because once it's in a black hole, it's not going to get out. The only thing that gets out of a black hole is gravity, except for a few little fiddly particles that Stephen Hawking talked about once. So in this case, what you're doing is you're converting orbital energy into gravitational waves. The first is a quote from one of the principal authors. The beginning of gravitational wave astronomy. They have detected other events since this one. We just haven't had time to analyze them. They're not as powerful as this one. Having two black holes coalesce is probably a relatively rare event, but we have a whole universe to look in. So they thought they would have to keep this thing running for a couple of years before they detected the first event. And they detected it serendipitously 50 minutes later. So there's going to be some good things coming out of gravitational wave astronomy. 2 more gravitational wave observatories are being built elsewhere in the world, one in Japan and one in Italy. And when you have 4 of them, you're able to zero in on the position of the object a little more closely. We have already mentioned that we were surprised at the mass of the black holes. It's mostly in the southern hemisphere, but they zeroed it down to 590 square degrees since then. And if you want to go looking for it, you'll have to travel south, but it's somewhere in there with a high level of probability. Oh, when we go down to Arizona, we can see down to about here. So maybe we'll go looking for it. Would you say 10? Probably not. So this science, the astronomy part of the black hole, didn't come out of the news media very much. There were some things like the size of the black hole being a bit of a surprise, but the fact that you're actually seeing something happening inside a black hole, now they're talking about if they can get really sensitive telescopes to be able to see some evidence of the gravitational wave generated by the Big Bang. The thing is gravitational waves can be anything from a few kilometers in wavelength to a wavelength equivalent to the size of the universe. So you've got a lot of looking to do, especially for the big ones. Just a quick note about what LIGO is. It's actually a Michelson interferometer. So you send a light beam down through this beam splitter, and half of the beam goes that way and half of the beam goes that way. It actually makes about 72 trips back and forth, and then they're compared. Well, we come back into the detector here. Well, light has a constant speed, but the size of the universe isn't constant, and time in the universe isn't constant. So the gravitational wave upsets time and it upsets distance, but it doesn't upset the speed of light, which is why we're able to detect the shrinking and expansion of space-time by testing it with a light beam. Anyway, these things make about 72 trips back and forth, and then they're compared in here. Well, if nothing changes, you can set those 2 light waves so they interfere destructively, so that the crest of one light wave is in the trough of another one. It's both the same wavelength of light because it's coming out of a laser. They cancel each other out. If something disturbs that balance, on one or the other of these arms or somewhere in between them, then those light signals are not going to cancel each other out. And by sophisticated use of that kind of technology, they're able to detect changes in space-time that are smaller than the size of an atom. We're talking about now throwing a couple of them out into space and having a much longer baseline, a much more stable environment. But, well, it remains to be seen how many of them are going to get the Nobel Prize out of this. The range of the current setup is about 226 million light years distant, so we're by no means sampling anything more than a nearby part of the universe. It's interesting that the mirrors that they use in this thing to reflect these beams back and forth are the best in the world. The 100 millionth of an inch. I didn't take the time to convert that to millimeters. Let's say 100 millionth of a millimeter. Close enough for astronomical. Now when we're dealing with superlatives, NGC 4889, which is this nice big galaxy here, has just been determined to have a 21 billion times the mass of the sun in its central black hole. The event horizon, the edge where light can escape and can't escape, is 5 times the orbit of Pluto. This is, I usually say when you fall into a black hole, it's going to rip you apart because of the difference in gravity between your head and your feet. But when you have an event horizon that big, you can fall into it. It's going to be a pretty gentle fall. For a while. Time stops inside a black hole, so it could take forever. You can just sort of imagine looking out and seeing somebody trying to wave to them, and they can't see it, but I don't think it works. The thing about this black hole is very quiet. It's not doing anything, it's not erupting, it's not sending out great gouts of energy. So it looks like it's pretty much swallowed everything in this galaxy that it can, and just waiting for some little errant spacecraft to come by it and suck up a little bit. This is the ever-ready bunny that never stops. It's on its 7th year now. Its 7th Mars year. It's on its 12th Earth year. This is meant to last for 6 months. It's worth reading the book of the fellow that built it, because he fought NASA long and hard to build extra redundancy into this thing. So anyway, it's sitting in a valley next to these hills in Mars. These don't mean anything to me. They could be Bradley landfill as far as I know, but they don't. We got a little gust of wind a month and a bit ago that blew some of the dust off of the solar cell, which is a big problem on Mars. The dust gets on the solar cells and you don't get as much energy. And typically when Mars is in winter, which it's coming out of now, it's too far from the sun for these space little rovers to get a lot of energy. So this one, by cleaning off the solar panels, gave a little extra energy. So it's actually been working through the winter in this thing called Marathon Valley, named for the fact that it's the same distance from its starting point as the marathon distance. And what you're finding is speck-type clays, which are clays that absorb water, and they're in such a shape, and there's many kind of chemical configurations with it, but more evidence of water on Mars. The main reason I brought this is for Gail, because speck-type is most familiar to us as this little product. I could have brought some along, but the cat.
So Mars is a big cat box?
I wasn't going to say that. Remember a couple of months ago I talked about globular clusters and how they all tend to have the same age of around the 12 or 13 billion or 11 or 12 billion light years, because they're big balls of stars that, obviously you got a big ball of stars, they must have all formed at the same time. But when we look at the inside of some and possibly all globular clusters, we find that they don't seem to have one age. Instead, in these samples here, which are all Magellanic Cloud globular clusters, one has 3 different age populations, and 2 of them show 2 different populations. So if you used up all of the dust and gas the first time you formed stars, and if you didn't use it up, you blew it away when the stars formed, then where did it get the dust and gas to form a new population? Well, they say that's easy. There were supernovas in these things. They blew their stuff back out into the interstellar medium, and that leftover stuff got collected up again and formed new stars. Well, here's a picture of one of these globular clusters, and here is the Hertzsprung-Russell diagram, which I'm not going to go into. Yes, sir?
Yeah, just, sorry, but going back to black holes and gravity waves, isn't it possible that you're able to get gravity wave detection from interacting bodies? Because at the point where they interact, you get the escape velocity of the gravity wave. Whereas perhaps a singular black hole, you may not be able to detect it with something like LIGO because it's engulfing so much space and time that the gravity wave can't escape it without having an interaction with another
Well, gravity waves don't, I mean, the black hole is gravity. The waves are generated, they're not subject to the constraints of the
There's no
light radiation.
within a black hole that would cause an emanation of a wave at all.
No, I don't think so. But if you're dealing with a higher level of physics than we cover here, but I'll talk to you about it after when we get to the break. Anyway, back to Hertzsprung-Russell diagrams. This is the collection of stars that, when you saw the Brendan, it was a long axis of stars that went up a graph like this. Well, those are stars that are on the main sequence. They're burning hydrogen, they're pretty stable, they have a long life, which is what we're doing with our star. But as they age, they swell up, they become cooler and redder, or hotter and redder initially. But anyway, they start to move off of this main sequence. You can see how this graph of stars on the main sequence has got this piece that's turned off here. And then there's other stars up in through here. So these are stars that have swollen up and become first cooler and then hotter and become redder. But if you look at that, you see there's other stars here that don't follow this pattern. There's one here and there's a bunch of stars that come up this way. And they look like they're on completely separate Hertzsprung-Russell diagrams. So what they've done is modeled the pattern of these stars based on, they just test a whole bunch of ages until they get one that fits. And so they come up with 9.5 billion years for the red line, 8.9 for, say, 9 and 9.7 for these two. Not a big difference, but enough to show you that certainly in a half a billion years, there were 2 or 3 episodes of star formation. And the other globular clusters, perhaps a little cleaner. Here's this one, which is turned off the main sequence here, but we've got these other scattered ones. Not a large number of them, but nevertheless, other stars that have gone on a different path here. Now, up till now, we haven't been sure where it came from, but the authors of this paper suggest that as these globular clusters pass through the Milky Way, which they do in their orbits, they run into gas clouds along the way and suck up some of the gas from those gas clouds, and they calculated how much they could reasonably expect to suck up, and sure enough, it's enough that it could account for these multiple generations of star formation within a decent-sized globular cluster. Here's a nice picture. I put this in because it's pretty. It's a IC image catalog, 2631 number. We have a reflection nebula and an emission nebula in it. A bright star here that's reflecting the light from this blue star is reflecting off the dust and gas here. And so it's like having a mirror there, so you see the blue color of the star. But up in here behind this gas cloud is another much brighter star that's causing the gas up in here to fluoresce. And so you end up with the reddish glowing color, just like a fluorescent light. It's a T Tauri star, which is a very young star, just basically in the process of collapsing down to becoming a main sequence object. And so what we're seeing here is the birth of a new star in this area, and somewhere behind the dust and gas is a an older and brighter star with a lot of ultraviolet radiation. Nice little picture from Cassini looking edge-on in the F ring there and looking at the disturbances in the F right here. Now normally we see these little wave disturbances from what are called shepherd moons, which are two little moons that go on each side of the ring and hold it in place. But in fact, these ones are caused by these little guys here, which are much smaller, that have actually passed through the ring in their orbit and stirred it up a little bit, kind of like having a nice calm little pool of water with mud on the bottom, and you throw a stone in it, you see the mud rise up. And so what's happening here is these little tiny moonlets, they go looking for these little disturbances. Here's another one here. Of course, Saturn's rings have got particles in it of all kinds of sizes. Next good news, they put the last mirror into the James Webb Space Telescope. And each one of these mirrors, when they launch it, is going to be made up of very, very accurately positioned by the software in it. There's 18 mirrors in this system. Here's the Hubble, and this is the setting of James Webb. Each one's a 1.3 meter telescope. And so the Ariane people, the Europeans, they say this year they'll be launching this. Eventually give us a 6.5 meter. So stay tuned for a couple of years from now. Let's give it the usual slippage 3 years from now.
So this means
Add a billion. And finally, Rosetta. Comet 67P is now moving away from the sun. The emission of the tail and everything else is still going on. In fact, there's some nice amateur images of it, but it is gradually getting away from the sun. And Rosetta will eventually be, they're going to say crash into it, but they're going to just lower it down gently onto the surface if they can. If it happens to be a crash, it's a crash. But if the cameras keep on working once it's down there, it ain't even there. So it's now rounded the sun, heading back out into the solar system. Recently detected water ice on it. We knew there was water there because they can see it in the gases in the tail, but they've never seen it on the surface. But now some of this dust and regolith that's on top of all of the ice that's underneath has been blown away a little bit by some of the jets of material coming off, and we've been able to get a look at it. And I put this one in because I couldn't get a cat picture, but I got a dog picture. It struck me as this thing looks like a dog with a nose and eyes and so Gail, I couldn't get you a cat. But I'll let Gail bring her own cat for us. Now I've got to find your present. Ah, here we are. Answer the cat.
Can you hear me? Cancer the crab has usually been seen as a hard-shelled animal. We don't know how long it's been a crab, but in Babylon and Egypt around 4000 BC, it was a tortoise. Then 2,000 years later, it was identified as a seraph beetle. Through the years, it has also been a lobster and an octopus. A tortoise, a lobster, and a crab all move with an awkward scuttling motion. When the sun is in Cancer around the time of the summer solstice, its northward motion slows, and it hesitates before it descends to its lower autumn and winter heights. Thousands of years ago, the sun was in front of Cancer the crab in its northernmost position. That was overhead then, at the latitude that we still call the Tropic of Cancer. The crab plays a minor role in the labors of Hercules. Hercules was the son of Zeus, the king of the gods, and Alcmene, who was a mortal woman. Zeus's wife, however, was the goddess Hera. Hera always hated Hercules, even though he was named after her. At one point, Hera cast a spell over Hercules so that in confusion he killed his own children.
For atonement, the gods commanded that Hercules spend 12 years in the service of King Eurystheus. The king assigned Hercules several tasks to perform. These tasks were so difficult that they seemed to be impossible, but the mighty Hercules accomplished them all. These tasks have become known as the labors of Hercules. The second labor that Hercules had to accomplish was to kill the Hydra. This was a snake-like monster with 9 heads. The crab was sent by Hera to distract Hercules in his struggle with the Hydra. The crab scuttled out of the swamp and began to pinch Hercules' toes with its claws. All during the violent fight, the crab was nipping at his feet. But Hercules was so mighty in strength that he finally stomped on the crab and killed it. Hera then rewarded the brave little crab by placing him among the stars as a reward for his service. Cancer, the crab, is small and dim, and to be honest, it really doesn't look very much like a crab. It's placed among Gemini to the west, Leo is on the east, Lynx on the north, and at the south we have Canis Major and the Hydra. The best time to see Cancer the crab is late January and early February. Cancer is the 4th sign of the zodiac, which I know we're not supposed to care about, but it happens to be my zodiac sign. Its name is from the Latin Cancer, literally the crab. So you might be led to believe that people born under this sign might be crabby. Cancer the crab's brightest star is Acubens, from the Latin name meaning the claw. This is a double star, white and red, so it's very patriotic, and the magnitudes are 4.5 and 11. The total magnitude is 4.6. People born under the influence of this star are supposed to be liars and criminals. Zeta is one of the most remarkable star systems in the sky. The total magnitude is 5.1. Both stars are yellow. It was discovered to be a double star in the year 1756. Then in 1781, Sir William Herschel turned his telescope to it, and he discovered a third component. The two main stars are a binary, and their separation is 19 astronomical units, which is about the distance between the Sun and Uranus. Both of these stars happen to be the same size and brightness as our Sun. Since that time, a fourth component has been detected, and a fifth is believed to exist. Cancer, the crab's main claim to fame, besides of course being my zodiac sign, is M44. This is the Praesepe, which is Latin for the manger, and we know it better as the beehive. This is one of the largest, nearest, and brightest of the open star clusters. It is clearly visible to the naked eye as a big fuzzy patch. M44 is 95 arc minutes across, 3 times the size of the full moon. It was recorded as early as 260 BC. The ancient people called it the Little Cloud. Galileo was the first person to turn a telescope to the Little Cloud, and he described it what he called a myriad of stars all buzzing around each other, and that is why we call it the beehive. There are more than 300 bees in this hive, and because it is so large, you'll get your best views of it with binoculars. Its brightest stars are 6 magnitude, and its total magnitude is 3.1. Very big and bright and very easy to see. M44 appears to be 800 million years old. It has a large number of blue stars, and a lot of them are variables. If you like variable stars, check out our Canopy. The brightest, it's easy to see it, magnitude 6.7, but then it dims to 11.8. Then you'll have to wait a long time to see it again because its period is 362 days, almost a year. Among the stars of Cancer, the crab is a small grouping called the donkeys, which appear on the back of the crab's shell. Acylus boreali is Gamma, that's the northernmost donkey, and Acylus austral is Delta, that's the southern donkey. A Greek myth tells us that these donkeys were ridden by Dionysus and Hephaestus during the famous battle of the Olympians and the Titans. The Titans were the bad guys, and they could not see the Olympians coming, but they could hear the shouts of the gods and the braying of the donkeys, which for some reason frightened them so much that they ran away in terror. By way of honoring this achievement, Dionysus arranged for the 2 donkeys to be placed in the sky as 2 stars. They were placed one on each side of the Praesepe, the manger, so they will always have a supply of food. There is another open cluster in Cancer the crab, M67. This is one of the oldest known clusters that appears to be more than 10 billion years old. It contains nearly 200 white dwarf stars. M67 was discovered by Johann Gottfried Kohler sometime before 1779, but because his telescope was so inferior, he could not resolve any stars. Our friend Charles Messier independently discovered M67. He resolved it into stars and catalogued it on April 6, 1780. This is a very rich open cluster. It's just 1.8 degrees west of Alpha Centauri. It's a compact group about 15 arc-minutes in diameter, half the size of the Moon. It has more than 500 stars, which range in magnitude from 6 to 10, and its total magnitude is 7. So you'll need a little bit more power to observe this one than you did for M44. An interesting thing about M67 is that it is so far from the plane of the Milky Way. It's about 1,500 light years away. The majority of open clusters are somewhere along the plane of the galaxy. There is even a meteor shower associated with Cancer the Crab. It's the Delta Cantacribs, which is typically active from December 14th to February 14th. So if it was clear, you might get to see a few tonight or tomorrow. I don't think they'll look exactly like these. The shower peaks on January 17th, and the rate is only 7 to 10 per hour. So it's considered one of the minor showers. I think we saw 7 to 10, right? Are you done? There are quite a few galaxies in Cancer the Crab. Remember that we're just west of Leo, so this is the beginning of the region that's covered with galaxies. And you see 2775 is not very large, but it is fairly bright. Its size is 5.4 arc-minutes, and its magnitude is 10.1. This is a spiral with quite a bright core, and you can just make out its spiral arms. They're very tightly wound. And you see 2749 is 1.8 arc-minutes by 1.7 arc-minutes, and its magnitude is 11.6. This is the brightest in a group of about 10 galaxies that are just within a few degrees of each other. And you see 2752 is this one. It's 1.8 arc-minutes by 0.4 arc-minutes, and its magnitude is only 13.7. It's really nice, a nice little spiral edge on, but it is very faint. Right at the top of this picture is NGC 2744. This is a beautiful barred star spiral. You can easily make out its arms. It's only 1.6 by 1.2 arc-minutes, and its magnitude is only 13.5. These are about the limit of what I can see with my 8-inch dog. This one is NGC 2608, which is 2.2 by 1.4 arc-minutes, and its magnitude is 12.3, so it's a wee bit brighter than the 3 we just looked at. Isn't this a good one? So even though the Crab's galaxies are small and faint, it does have those great open clusters, which, you know, always will make me happy. So if it's ever clear and it ever warms up, get out there and take a look at Cancer the Crab.
Thank you, Gail. Well, I guess it's time we stop for coffee, and thank you, Sylvia, for keeping the show together again for us. And let's come on down and help yourself.